All right, part 2, a video review of the properties of logs. These are going to be essential to us when we start working on the derivatives of functions that include logarithms. So exponentials and logs are inverses of each other when their bases match. So other sets of inverses that we have in mathematics: addition and subtraction, multiplication and division, squaring and square roots, cubing and cubed roots, sine and sine inverse, tangent and tangent inverse, cosine and cosine inverse. I think that's it for now. Well, for our math repertoire at this point in our math lives. We can think of this roughly in terms of one undoing the other. So if you were to add 5 and then immediately subtract 5, you get right back to where you started. Likewise, if you were to multiply by 2 and then immediately divide by 2, you would get right back to where you started. If you squared something and then immediately took the square root, technically you get the plus or minus version, a little nuance to be careful of, but you get the idea. So try simplifying these. Well, exponentials, something that has an exponent on it, and logs are inverses. Logarithm, exponential, both have a base e. Cancel, cancel. The answer is 3. E, natural log. Exponential, logarithm, cancel, x plus 1. Final answer. Because logs are derived from properties of exponents, their properties are those of exponents as well. So thinking back to previous classes, if you have the natural log of 2 arguments multiplied together, you can break that up into the natural log of x plus the natural log of y. Because if you had, I'm going to use e for our base because that's our nice base. If you had e to the x times e to the y, that property would say e to the x plus y. So our multiplication turning into addition is related to the properties of exponents. Next one then, when you have division of 2 variables, or 2 terms rather, you can take that and take it the natural log of x minus the natural log of y. And this works because if you think about e to the x over e to the y, we would do that by taking e to the x minus y. Last one then, the natural log of x to the nth power. So raising something with an exponent, you can swing that n down in front. Okay, so n times the natural log of x. This one is similar to if I had e to the x to the nth, I would multiply e to the x times n. From here then, I want to make sure that we're clear. This only works if your argument that's inside of here still fits the domain. So we have to be careful because our domain values for the natural log function are real numbers that are greater than 0. So make sure that when you do the swing down in front, whatever's left on the inside still makes a valid argument for the natural log. All right, some problems to try. Write the expression as the log of a single quantity. So you're going to start and we're going to work backwards. I'm going to do one, then you're going to try the second one. So working backwards, I can move this 2 up to a power. And I can move this negative 1/2 up to the power, or I can leave it as a minus and just swing the 1/2 up, which is what I'm going to do for now. It won't matter in the end, okay? Just changes being in the numerator, denominator, thinking about subtraction, division. It all comes out okay, I promise. So from here, this will be the natural log of 9 minus the natural log of the square root of x squared plus 1. Well, this subtraction then can turn into division. The natural log of 9 over the square root of x squared plus 1. Notice that I wrote this as the log of a single quantity. So I only write the log part once. And this then is one giant argument that's inside of that natural log. Okay, I'm going to have you pause your video and try number 2. Pause now. All right, this is the order that I chose to go in. When I mentioned earlier about swinging the negative up and how it won't matter, let's say right here you decided to move that negative up, you would end up with the natural log of x squared minus 1 to the negative first. And then at the very end, anything that has the negative exponent, you would push to the bottom. So that can still work out. Another thing to note, I left this as to the 1/3 power, but you could have rewritten this as the cubed root of that whole thing. But we have met the criteria. We have a single logarithm of a single quantity. All right, let's use those properties of logs to expand out. This is going to be what is super critical when we want to find derivatives, okay? So instead of just taking the derivative of this, I would use log properties first in this way. So I'm going to choose to see this as the natural log of x times x squared plus 1, all of that to the 1/2 power. So I can swing the 1/2 down in front and then break up the multiplication into addition. And then the final step, I could distribute in this 1/2, but you don't have to, because eventually, if we're talking about calculus, we want to leave that 1/2 out in front because that constant multiple rule will benefit us. Okay, go ahead and pause the video. Try the next one for yourself. Pause now. Go ahead and check that final answer. We broke up the multiplication, we broke up the division, and we dealt with all of these exponents swinging down in front. All right, thus concludes your review of the properties of logarithms, which again will be critical when we start finding derivatives.